Hey everybody, and welcome back to Patel Academy. Today I want to cover the AP Physics C Mechanics 2019 free response questions from Set 1 in order to give you guys an idea on what type of content could come on the upcoming AP exam, as well as give you an idea on some of the major concepts and some small errors that students have made so that when you guys are writing your AP exams, you guys don't face the same situation. And you guys are able to answer all the questions quickly and efficiently while still being accurate. So let's get right into it. Now, I do want to make a note that the time limit for the AP Physics C Mechanics questions, there are 3 total long answer questions, and the time limit is 45 minutes. And so that is a time limit that I will try and follow. However, if I go a little bit over, then that's because I'm explaining things. And if you guys follow a similar pace like me, then on the actual AP exam, you guys will definitely be able to meet the time limit. So let's get right into it with question number 1. So question number 1 says that in an experiment, students use video analysis to track the motion of an object falling vertically through a fluid. We have a mass of 12 grams, and it's released from the top of the fluid, and it's moving downwards. Now, we're given a VT, or a velocity time graph, and it shows a curve of best fit with all the different data points that were tested. So question number 1A, part 1, says, does the speed of the object increase or decrease, or does it remain the same? Alright, so on the side over here, I'll just write question 1A, and then part I. Okay, so does the speed of the object increase, decrease, or remain the same? Well, if you look at the velocity time graph that we're given, well, speed is just the magnitude of velocity, right? And so what we see is that when you look on the curve of best fit, that magnitude of velocity, or the value of velocity, is increasing as we move forward and forward in time. And so what that shows is that the speed must be increasing, right? Keep in mind that speed is independent of direction, and so we just care about the actual numerical values. We don't need to interpret it in context based on the direction or how the object is traveling, and so the quick answer is just that it increases. All right, part 2. So part 2 says, in a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changes or changed as the object fell. All right, so what do we know? Well, we know that the object is falling, so it's moving downwards, and so the velocity must be pointing downwards. We also see that because the speed is increasing, the magnitude of velocity is increasing, and keep in mind this can only happen if the velocity vector and the acceleration vector are pointing in the same direction. And so because of that, we know that the acceleration is downwards. Now about the magnitude of acceleration. Well, keep in mind that acceleration is also the derivative of the velocity function, right? So at any given point, it's the slope of the tangent to the curve. And so if we see the slope of the tangent as it changes over time, we see that it goes from very steep to less and less and less steep. And so because of that, what we can say is that the magnitude is decreasing. Or you can interpret it in terms of the actual change in velocity, and you can see that the velocity is rapidly growing at the start, and then starting to follow more of a linear pattern, so a slower growth, and it will, based on this fit, it will level off eventually. And so we can use that information to say that the acceleration, the magnitude of acceleration, is decreasing. Alright, so that was part 2, and now talking about part 3. It says, calculate an approximate value for the magnitude of the acceleration of the object at time t equals 0.2 seconds. Okay, so keep in mind the idea of acceleration being the slope of the tangent. Essentially what we have to do is we have to graph a tangent line at the point t equals 0.2, and then we have to find the slope of it using 2 points on the tangent line. Now, because I don't have the actual graph on the side over here, I'm going to try and do a rough drawing of the graph and the tangent line, but I'll tell you the specific points that I would have used if I had drawn an accurate graph on the paper as well. So you guys can try and follow and see if you get those same points. So if I make a quick drawing like this, the graph is kind of like, kind of follows this shape. And so if I utilize this tangent line, where this is t equals 0.2, then when I look at the point that I get over here, I get the point 0.14, 0.6. And then the point here that I would have got, keep in mind I'm trying to get coordinate points, so points that lie on the grid, not in between, because it's very hard to get an accurate measurement for those. So I would have gotten 0.25 and 0.85 as my other point. So it is 0.25, 0.85. And so I'll switch back to white over here. So the slope, keep in mind that in this case, well, it is delta y over delta x, so it's the change in y over the change in x. I'm going to write it specifically as delta v over delta t in this case, because we are finding acceleration. And so this is equal to 0.85 minus 0.6 over 0.25 minus 0.14. And so putting this into my calculator, I should get the value 2.27. And keep in mind that the units would be meters per second squared. And so the reason why is because we're essentially measuring the change in velocity, so the change in meters per second every second, and so the units just become meters per second squared. All right. So for question 1b, part I, so we're given an equation for velocity modeled by the constants, the coefficients a and b, and it's an inverse exponential. So it's a times 1 minus e to the power of negative bt. And it says to derive an expression for the magnitude of the vertical displacement y at t of the following object. Okay, so what do we know? When we're given velocity and we want to try and find the position or the displacement, we take the integral, right? So we know that y at t equals the integral of v at t with respect to time. And then keep in mind that because this is an indefinite integral, so we're just trying to find it overall and not between two timestamps or boundaries, we will need a condition, preferably an initial condition. And so one of the things to consider is that if you use a point on this curve of best fit, it's not going to be the exact time function. And so what you have to utilize is what exactly do we know about the position that's guaranteed going to be true regardless of the experimental error. That's that at position 0, at time 0, sorry, the position is going to be 0. And so we also utilize the fact that y of 0 is equal to 0, and that's our initial condition. So now we can go ahead and utilize this velocity function to integrate, and so we get y at t is equal to the integral of a times 1 minus e to the power of negative bt dt. And so this should be something that you guys can integrate fairly quickly. I'll pull a constant out, so I get the integral of 1 minus e power of negative bt dt. And so keep in mind that this a is going to multiply to every term within this integral. And so this first term is going to be at, right? Because the integral of 1 is with respect to time is t. For the second one, I'm going to have minus a. Now the integral of a function, of an exponential function with e as the base, is just that function repeated. And then because we're taking the integral, we have to use the inverse chain rule. So we divide by the derivative of the inner function. And so what you'll get is that it's minus a times e to the power of negative bt, and then divided by negative b. And then remember, we have a plus c. If you guys don't understand the inverse chain rule, then just apply a u substitution so that u equals negative bt, then du will equal negative b, and then you just perform the integration with that u substitution and then bring it back to the t world. And so now if I'll simplify by canceling out some of these negatives, I get at plus a over b e to the power of negative bt plus c. And so keep in mind that, so this is y at t, except we also have our initial condition that we have to use to solve for c. And so we get y at 0 is equal to 0. So when I plug in 0 into each of these, right? So a times 0 is going to be 0. A over b times e to the power of 0 is going to be a over b. And so what I get is 0 is equal to a over b plus c. And so c is equal to negative a over b, right? And so using this information, I can write out my final y at t expression. So y at t is equal to at plus a over b e to the power of negative bt minus a over b. Now this should suffice, but if you did want to convert it into numerical values, then we can make all the substitutions. And so the answer that we should get is using a as 1.18, 1.8t, and then plus 0.236 e to the power of negative 5 t, and then minus 0.236. And so, well, I believe AP does allow you to keep the A and the B without making the substitution. I personally prefer to make these substitutions, and to be on the safer side, you're not going to go wrong with the numerical values. So I would do that just in case. All right, so that was part B, or question 1B, part 1. For 1B, part 2, so that looks really bad. It says derive an expression for the magnitude of the net force Ft exerted on the object as it falls through the fluid as a function of time. All right, so what do we know? Well, we know that F at t is going to be equal to the mass, which is constant. Sorry. So mass is constant, and then times the acceleration. This is just Newton's law. And the acceleration is going to be non-uniform. And so we need to consider it as a function of time. And so we can rewrite this as m times the derivative of the velocity function over time, which is just m times d over dt of v at t. So what this tells us is that we just have to take the derivative of this velocity expression and then multiply it by the mass. And so I get f at t is equal to, well, it's m times, now what's the derivative of this velocity function? Well, I know that I'm going to have a times, well, this, so the a can come out of the derivative expression because it's a constant. Now we want to take the derivative of this inside, 1 minus e to the power of negative bt. And so the derivative of 1 is going to be 0. The derivative of negative e to the power of negative bt is going to be b times e to the power of negative bt, which is equal to a b m e to the power of negative bt. Keep in mind that when I took this derivative, the negative e to the power of negative bt turns positive because we multiply by the derivative of the top. So we have negative times negative b times e to the power of negative bt, and so it becomes positive b. And so once again, while this final answer should be enough, if you did want to plug in the numerical values, put it in my calculator, so I get 1.18 times 5 times 0.012. Now keep in mind that this is because the mass was 12 grams, and so we need to convert it into kilograms, and so I get 0.0708, or I'm going to round that to 0.071, e to the power of negative 5t. And so that is how you would solve this problem. Okay, so moving on to question 1ci. Now for this problem, the way that I like to solve it is I'm comfortable with using limits, and so whenever it asks you to determine the constant speed of an object, it's really easy for you to just calculate the limit as time goes to infinity, because as we saw in the graph, or as you can probably interpret from this being a reciprocal exponential function, it will level off over time and it will have a horizontal asymptote as time goes to infinity. And so the easiest way that I think you can do this, now I'm not sure if AP necessarily accepts this method, but it is one of the easiest ways to do it. And so all I do is I take the limit as t goes to infinity of v at t, and what you'll get is that, so as t goes to infinity, e to the power of negative bt will go to 0, because if you rewrite that, you'll find out that it's 1 over an exponential function. So it's going to be 1 over infinity, which is 0. 1 minus this 0 term is 1, and then times a, you're just going to get a as your answer. So this is going to be 1.18 meters per second. So I find that this is probably one of the easier ways to solve it, as long as you understand the concept of limit, because essentially what we're saying is that because we have an algebraic function, in order to solve this, what we can essentially do is we can just identify the general trend mathematically as it goes to infinity. If we look at the next question, I'll switch the slide. Okay, so this one says determine the force exerted by the fluid on the object at this time. So by this time, what they mean is when it reaches a constant speed. And so this one is a little bit tricky, because you have to think about what forces necessarily are being acted upon and what our initial force expression represents. So I'll give you guys a moment to think about that, and then I will move on to solve. And so keep in mind that originally what we had was, we had F at t as being our net force based on the acceleration, right? So it's net force. But what exactly is our net force in this case? Well, if we look at the diagram, right? Now this would be a little bit easier if you, the question kind of gives it away, because it says the force exerted by the fluid on the object. And so what you should know is that because we're moving downwards, we always have our force of gravity, but then there's also a resistive force, the force of fluid. And if you guys have studied fluid physics, then you guys would know that there is a force of the fluid that has its own set of formulas, but for this case, we're just interested in calculating our net force. And so what do we know about F at t? Well, using the definition that we did earlier, this is m times a at t, and I'm going to write this as mg minus the force of the fluid, and then this is also m times dv over dt, which is equal to mg minus the force of the fluid, right? And so what we know as well is that what exactly is dv by dt? Well, this is 0, right? We've reached the point where we have a constant speed. And so what exactly does the constant speed represent? Well, the constant speed just represents that there's no change. So keep in mind that dv by dt represents a change in velocity. There's no change anymore. And so that entire left-hand side will become 0. And so what we're left with is 0 is equal to mg minus the force of the fluid. And so my force of the fluid is equal to mg. I'm going to use 0.012, and then I'm going to use gravity as being 10. It makes it easier, and so I get 0.12 newtons. Alright, so the justification in here, you would get points for recognizing that the change is 0, and so your net force statement will, or because there's no net force, there has to be a constant velocity. If you even recognize that principle, then you would get full marks for this if you didn't write out this algebraically. So you just have to recognize that the force of fluid is equal to the weight of the object, and then calculate what the weight of the object is. yeah. Moving on to question number 2. So hopefully guys, you have been able to follow along with my explanations. At the end, I might go back to some of these questions if there are any specific ones that might require a little bit more clarification, and I will make sure that I go through that clarification with you guys. All right, so question 2A. So we're given that we have a pendulum of length L that's swinging, it hits block 2 moves off the table. We're given some values on all of these different heights and masses, and we're said that we have to express all the algebraic answers in terms of m, L, and physical constants as appropriate. Okay, so question A says determine the speed of block 1 at the bottom of its swing just before it makes contact with block 2. Okay, so whenever I think of something like this, a scenario like this where there's a pendulum suspended in the air and it's moving, I immediately think about conservation of energy. It's probably the easiest way to approach a problem like this. So let's consider K initial plus U initial is equal to K final plus U final, right? Okay, we know that I'm going to choose my frame of reference to be the tabletop, okay? So I'm not going to consider it to be the floor in this case. Remember, you can choose your own frame of reference depending on the scenario you're working with. So I'm going to choose it as being the tabletop. So what we know is that at the time when it's suspended without moving, there's no kinetic energy. And when it's at the very bottom, so when it's basically on the tabletop, there's no potential energy. And so what we get is that my mgh is equal to 1/2 mv squared, and so my v is equal to the square root of 2gh, right? Except h is not a physical constant that we're allowed to use. So what exactly is the h in this case? Well, the height, if I'll draw it on this side in blue. So if we have our pendulum like this, and then it shifts down, right? Something like this, well, what's this height? It's L, right? It's just the length of the pendulum. And so our final expression for V is equal to the square root of 2GL. And that answer will work. Okay, part B was a very simple question. It just says before block 1 hits block 2, what forces are being acted upon it? Well, if you look at this end scenario, right, we see that it is suspended in the air, and so there is going to be a force of gravity. So I'll draw our dot right there, and I'll say that there is going to be a force of gravity. Or I'm pretty sure the AP exam lets you write mg as well as the force. You don't necessarily need to indicate it as fg. But then there's also going to be a force of tension bigger than the force of gravity. Sorry, my thing isn't very straight, but there is going to be a force of tension. Why? Because the object is being suspended in its circular motion by the pendulum without falling off, right? So if you look at the diagram, it hits block 2, it's still suspended in its pendular motion. And so because of that, we know that there has to be a force opposing gravity to make sure, and greater in magnitude compared to gravity, to make sure that it stays within its path without just falling off, because that's what would happen. The string would break if the gravity was too large. And so because there's a string, technically we already know that there's a force of tension. It's larger than gravity because the string doesn't break. All right, and so now I'll try and fit part C on here as well. It says derive an expression for the tension Ft in the string when the string is vertical just before block 1 makes contact with block 2. Okay, so this one should be fairly simple. It's just using Newton's second law, but keep in mind that it is a pendulum, and so if you look at the motion of the pendulum, it follows a circle, right? And so we have to utilize, and also all of our forces are pointing towards the center, so that should be an indication that it's uniform circular motion. And so we still write our F net is equal to MA, which is equal to, or in this case it would be MA sub C because it's centripetal acceleration, and then our net force is Ft minus mg. All right, and it's ft minus mg in this case because it's just before block 1 makes contact with block 2. So our force pointing towards the center is ft, pointing away is mg. Okay, and so m v squared over r, right? So that's centripetal acceleration is equal to ft minus mg, and so I'll write it to the side. ft is equal to mg plus mv squared over r. Alright, except we have a lot of constants that we have to plug in terms of the constants we're allowed to use, or in terms of the values we're allowed to use. So we get ft is equal to, okay, so what's this mass? Now in the first question, in the first part, if you noticed, I just left mass. I didn't actually substitute for what values they gave because the mass is cancelled out. In this case though, we have to be careful. It says that block 1 has a mass 3 capital M. So we have 3 mg plus 3m times, what's our v? Well, it's the square root of 2gl squared over L, right? And so if we simplify this, we get 3mg plus, all right, so the square of a square root is just the inner portion, so we get 2gl, and then the L's will cancel out, and so we should get 6mg left. So this second expression would simplify to 6mg, and so our force of tension is 9mg. Alright, and so that is part C. Alright, so moving on for part 2D. It says calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. Alright, so what we know, so we know that it follows something that we've seen in terms of projectile motion, right? Because it's a purely horizontal velocity that we have, and we're traveling a distance of 4L and a height of 2L. And so it says calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. Okay. Before I work through all the kinematics, I am going to just solve for some of our physical constants because it says that the length of the pendulum L is 75 centimeters. So the height of the table, H, is equal to 2L, which is equal to 1.5 meters, right? 2 times 75 is 150, so 150 centimeters is 1.5 meters. Our delta D, or our displacement, you can write as delta X as well, is 4L, so this is going to be 3 meters, twice as much. And so what we know now is that we can use our kinematics equation to calculate the total time it takes for the object to travel the height of 2L. And so keep in mind, what is the kinematics equation that we can use? Well, delta D is equal to V0T plus 1/2 AT squared, right? Okay. Now what exactly is our delta D? Well, we're traveling a total of 1.5 meters down, so we get negative 1.5 is equal to V0T, or V0 T, sorry. Our initial velocity is 0, right? So before our collision, just before it, so right when it leaves the table, it's on the edge of the table. So it actually starts out with a velocity 0 plus 1/2 GT squared. All right, and so what we get is T squared is equal to 3 over G, right? I multiplied, or sorry, this should be negative 3. Okay, here's where I should probably point this out. It depends on what convention you use. So because I actually made an error over here. Because I set my displacement as negative, so it's traveling negative 1.5, I actually need to include a minus here because G would be negative because the acceleration is downwards. so g would be negative. And so I get t squared is equal to positive 3 over g because the negatives cancel out. And so I get t is equal to, sorry, I'll just write it on the side so I have a little bit more space for the next question. T is equal to the square root of 3 over g. And so, while you should be able to leave it like this because it said that you can leave your answers in terms of physical constants, if you did want to solve, you should get, I'll plug it into my calculator, something like 0.55, I believe. Square root of 3 divided by 10. And I get 0.547. So I'm just going to round that. 0.55 seconds. Alright, so that was part D. Now for part E, it says calculate the speed of block 2 as it just leaves the table. Okay, well this is just, again, using projectile motion. We know that horizontally we only have one equation really that we use, and it says that Vx is equal to delta D over delta T. Well, we just figured out what a delta T is, and so we get our distance as being 3 meters over. Now, if you want it to be precise, I would actually use square root of 3 over g. So when we simplify this, we get 3 square root g over the square root of 3, which is equal to root 3g, I believe. And so solving, I get square root of 30, which is 5.47. Sorry, meters per second. All right, because we're calculating the speed. And so if you want to know what I did over here, so when I divided by root 3 over root g, so yeah, root of 3 over g simplifies to root 3 over root g. And then I just worked with the fractions. When I divide a fraction, I multiply by its reciprocal. Then I just rationalized. So I multiplied the numerator and the denominator by root 3. And then I canceled. And so I get, in the end, the square root of 3g. And so solving, I get 5.47. This was using g equals 10. If you use g equals 9.8, you would get something like 5.45, I believe. Both of them should be acceptable. And I think if you leave it as a square root of 3g, you should still get the credit. You should still get credit as well. All right. 2F. It says calculate the speed of block 1 just after it collides with block 2. Alright, so what do we know over here? Well, the wording used there, the word collides, should be a pretty good indication that, well, a collision involves conservation of momentum. And so if we set that up, we see that our P1 plus P2, this is initial, is equal to our momentum 1 final plus our momentum 2 final. This is just how I like to set it up. If you don't set it up like this, that's okay. You can calculate the initial individually and the final individually as well. So when we consider, now keep in mind that this isn't, the two objects don't stick together, and that's why I wrote P1 and P2 are the momentum of 1 and the momentum of 2 final as separate things, because they don't stick together. If they did stick together, then you'd have to combine the masses because they would have the same final velocity. So what do we know? Well, this is M1 V1 plus M2 V2. This is all initial, by the way, equals M1 V1 plus M2 V2, this is all final. And so what we know is that the mass is 3m. Our velocity just before the collision we found out was the square root of 2gl. Plus, what do we know about the mass of block 2? It has just a mass capital M, and its initial velocity was 0. Now the masses stay the same. We want to find this value V1, and this next one is M, and then keep in mind that at the very end while projectile motion was occurring, we found that the horizontal velocity, which is all that the block would possess when it gets hit off the table, in the beginning it only possesses horizontal velocity, and that we found it to be the square root of 3g. And so yeah, I like to be really exact with my answers, so I didn't include the decimal equivalent once again. So what I see is that this m times 0 will go to 0, and so I get 3m square root 2gl is equal to 3m v1 plus m square root 3g. The m's can cancel out. I'll show that in orange. So what I'm left with is, if I try to isolate my v1, right, so I get 3 times the square root of 2gl minus the square root of 3g divided by 3 is equal to v1. That's just the algebra. And so you could leave it like this. I think we can substitute for L as 0.75 meters. And so we get 3 times the square root of, keep in mind this is 1.5g minus the square root of 3g over 3 is equal to v1. And so while this is an exact enough answer, I think it might be helpful if we just solve for this. So I'm going to put this in my calculator as 3 root 1.5. Sorry, I'm just going to write 15 directly because I'm using g equals 10 minus the square root of 30 divided by 3. And so I get the answer 2.047. So I'm just going to round that to 2.05. If you utilize g equals 9.8, I believe you should get something a little bit closer to 2.01. But still very similar answers. And so you know that the steps that were done, they do make sense. If you did want to simplify this, I'll just write it to the side over here. We could divide stuff by 3 and do it that way, or you could distribute this 3 inside the square root and then try and factor some stuff out. But overall, what I would leave it as is the square root of 1.5g minus the square root of 3g over 3. That would be my expression for v1. And that should be exact enough to get you full marks. Okay, for 2g, it says calculate the angle theta max that the string makes with the vertical as shown in the original figure when block 1 is at its highest point after the collision. Okay, so this is something that you guys should recognize on how exactly we can solve it, right? So this involves the height, and it involves the expression of L times 1 minus cos theta. If you haven't seen this expression before, I highly encourage you guys to revise it. But I will try and show exactly how that comes. It just involves utilizing the height. And so what we consider over here is we do have conservation of energy still after the collision. And so we say that for K initial plus U initial equals K final plus U final. Now keep in mind this is directly after the collision that we're using. So right after the collision, our U initial is still going to be 0. And then at its theta max, this is going to be 0. And so we get 1/2 mv squared is equal to mgh, right? And so, well, the masses can cancel out. And so we're trying to solve for theta now. How do we introduce a theta value into this? Well, the expression that you may have memorized, I'll put that in blue to the side, is that, is like a note, h is equal to L times 1 minus cos theta. This is something I highly encourage you guys to just memorize, to plug it in. If I have time, then I will show you guys how you derive this at the end. And so what we get is v squared is equal to, v squared over 2 is equal to g L 1 minus cos theta. And so 1 minus cos theta is equal to v squared over 2gl. And so theta is just the inverse cosine of 1 minus v squared over 2gl. Right, and so what we can do is we can substitute the value of v that we got. And so what we should get is theta equals 43.94. Now, if it's a little bit easier for you guys to visualize, you guys can calculate the numerical value of k initial first using the speed of block 1 after it collides with block 2, so using the answer from part F. Then you substitute that in your u final to solve for h, and then directly solve for cos theta using that final equation. Or you can just plug everything in, get your actual expression, and then solve from there. I didn't work out everything exactly, but we would just have to use that v value. I would use the decimal one in this case because you don't want that that entire expression involving the 2 square roots and then having to FOIL stuff out or distribute or whatever. So I would just plug in the decimal value, and you should get 43.94 degrees. I just wanted to make a quick interjection over here to show you guys exactly why that h is equal to L times 1 minus cos theta formula actually works. So I'll write that down up here first. So we know that h is equal to L times 1 minus cos theta. I said it earlier in the video that I would show exactly how the proof came for why this works, but I forgot to do so, so this is the place where I'll show that. So let's say if we have a pendulum, right? And then it travels, I'll show it in blue, to some place, just like in the question that we had, something like this. And so we know that this value is theta, right? And we also know, so I'll put this in green, that this is L and this is L. All right, so why exactly do we get this above expression? Well, if you think about it, right, I'll redraw it over here. So keep in mind that, remember how we were looking at potential energy? So that requires a height. Right? And so we call this distance the height, except so now think about what happens right here. So this is exactly why we use where the cos theta comes in. If I draw a line, something like this, to create a right angle, right? We know that this is L, so this has to be L cos theta. We also know that this resultant distance is h, our height. Except we also know that the length of this entire string, as by the previous, is L. So we get L, so the length of the pendulum, is equal to h plus L cos theta. And so just doing some algebraic rearrangement, L minus L cos theta is equal to the height. And so L times 1 minus cos theta is equal to the height. And so that's how we can derive this formula. Now the sine version doesn't really come up because, as you can probably see, the sine component when you have this theta value isn't actually useful to put into context with the height, because it's perpendicular to the height instead of parallel, so that you can actually use this algebraic summation and this manipulation. So we don't usually use the sine theta value, but if the theta was at a different position, like the opposite, so if, for example, we were given, although I don't know why a problem would give this, but let's say if we were given some value beta, then we could use the similar principle of getting the component. So we'd get L sine beta plus h is equal to L. And so then we'd be able to solve in that way. So it just depends on which angle you're given. So I will do the beta example as well. So I get L is equal to L sine beta plus h, and so a similar thing, h is equal to L times 1 minus sine beta. So this is fairly explanatory as well. So yeah, those are essentially the two only cases where you would need to remember a formula like this. So whether you want to memorize it or whether you want to memorize how to derive it so you can do that on the exam, it's up to you depending on your time management. But I just wanted to put this in there. Let me check on how much time we're at. So we've solved 2 questions. I'm currently at 40 minutes, so it's a little bit extra, but that's because I have been explaining the things along the way. So you guys should be able to meet the 45-minute mark. All right, question number 3. This is where we get into rotational kinematics and dynamics. Okay, so we have a horizontal circular platform with rotational inertia I sub p that rotates freely without friction on the vertical axis, and we have a wheel. Now we're given that the wheel is a distance d from the vertical axis and exerts a constant horizontal force of magnitude F tangent to the wheel until the platform reaches an angular speed omega sub p. Alright, so and this occurs during time delta t, and it's constantly in contact, rolling or spinning without slipping. Okay. So it says derive an expression for the angular speed omega sub p of the platform. So that's after our time delta t. Express your answer in terms of all of these constants and all of these values. Okay, so what we're given is that we have a force of magnitude F tangent to the wheel. So I'm just going to quickly draw what that might look like. I'll use orange. So what I get is that we have our wheel, we have this distance d, right? And so because we have a force that's going to act at a 90-degree angle horizontal, this is kind of what it looks like. So that's the wheel, and we have a force. And so keep in mind that because we have a force acting a distance and it's not going into the center of the platform, so it doesn't pass through the center of the platform, we have a torque. And so that's exactly what we're going to utilize. So keep in mind the 2 different expressions that we can use for torque. So we have, I'll just draw this like this, I'll draw a better tau symbol. So we have tau is equal to I alpha, and it's also equal to R cross F, right? So those are the 2 definitions for torque that we have. If I just set these equal to each other, if I make the substitutions, I get I sub p alpha is equal to, now R cross F. We know that the magnitude of the torque, when you have a cross product, is going to be the magnitude of R times the magnitude of F times sine theta. Theta in this case is going to be 90 degrees. And so because it's 90 degrees, sine of theta is going to be 1. And so we just have RF, right? The magnitude of R times the magnitude of F. Now the magnitude of R is D, the magnitude of F is F. And so what we get is that alpha is equal to dF over I sub p, right? But we're not done yet because we have to find the angular speed of the platform. And so keep in mind, rotational kinematics, what we can use is this equation. So we have omega p is equal to omega naught plus alpha t. And so our omega naught, because we start off at rest and then we reach this angular speed, so we just have, this is 0 plus fd over I sub p times t. And so our final omega p value, omega sub p, is going to just be f dt over I sub p. Yeah, I use delta t because that's the total time that we were given that the force that the torque was acting on. All right. For part B, it says determine an expression for the kinetic energy of the platform at the moment it reaches this point. Well, that's fairly simple. We have the rotational kinetic energy is 1/2 I omega squared. So this is equal to 1/2 I sub p times f d delta t over I sub p squared. So working this out, we should get, I'm going to leave this part together because there's no cancellation, and then divided by 2I sub p. This is because in the denominator we have I sub p squared, and then we have in the numerator an I sub p, so they'll cancel, and we'll be left with just one IP in the bottom, and then we're multiplying by 1/2, and so that's how we get this final expression. Okay, part C. Alright, so it says derive an expression for the angular speed of the wheel when the platform has reached angular speed omega sub p. Express your answers in terms of these constants. Now this was an interesting question because it required you to make a connection that not everyone may have saw initially. And so what do we know? Well, I'll give you an analogy. Think about gears, right? So think about when there's two gears that are connected to each other that are rotating. The angular speed is going to be different because one rotation of a larger gear, or in this case one rotation of the platform, is going to occur at the same time as multiple rotations of the wheel because it's smaller, right? So it travels much faster. However, the distance traveled in terms of its circumference is going to be the same. So it's a thing that's a little bit hard to visualize, but because it's spinning without slipping or rolling without slipping, we can say that although the angular velocities are going to be different, their ratio is going to be linear. And because of that, it's linear dependent on the radius. And so what we can say is actually that the linear velocities are going to be equivalent. And so we get v sub p is equal to v sub w. For the linear velocity of the platform based on its circumference, it's going to be the same as the linear velocity of the wheel. Because while the wheel may have more revolutions, it still will travel the same distance in terms of its circumference as the larger platform, which will have less revolutions, but each revolution is going to have a much larger distance covered. And so remember that we can also use this v is equal to r omega for rolling without slipping. And this is just how you convert between the linear and the rotational analogs. And so we get r omega p is equal to r omega w. And so we're trying to solve for omega sub w. So omega sub w, sorry, I'll change that in the original. I don't want to get confused between w and omega. Is equal to r omega sub p over r. Should probably label. Which is equal to, okay, so what is the r, or the radius of the platform? Well, it's just d. What is omega p? Well, we solved for that earlier to get fd over ip, right? Oh, in this case, actually, I just reread the question. It says express your answer in terms of d, r, and omega p. And so we actually don't need to solve for omega p, or substitute for that. And so we just get d omega p over r, because r is the radius of the wheel. And so that is enough. If the question did include express your answer in terms of ip as well, then you would know that you have to substitute for omega p from question A, but they're lenient. Okay. Question 3D. It says that when the platform is spinning at this angular speed, the wheel is removed, we hold another disc with the same rotational inertia, and we release it from rest, and it falls onto the platform. After a short time, the disc and the platform have the same angular speed, omega f. Okay. So how exactly do we answer something like this? Well, remember that if we have two objects interacting with each other in a linear situation, we call it a collision and we conserve linear momentum. In this case, there's a collision, but it's rotational, so we conserve angular momentum. So keep in mind, angular momentum is L. So L1 initial plus L2 initial is equal to L1 final plus L2 final. Now in this case, what is true is that, so keep in mind what exactly L is, right? L is I omega, right? So that's just the definition of angular momentum. We could convert it to linear by saying that it's R cross P, but because we're staying within the rotational situation, it's I omega. So we also know that the speed is the same between both of them. So we could honestly say that this is, so I omega 1 plus I omega 2, this is the initial, is equal to IP omega final plus IP omega final. You could combine them and say that it's just 2 IP omega final because they have the same speed. So just like in conservation of momentum in the linear world, where we just combine the masses as m1 plus m2 times our velocity, you could do the same thing. It's just IP plus IP times omega final. But what we get is we can cancel out the IPs out of all of these, and so we should just get omega 1 plus omega 2 is equal to 2 omega final, right? And so now what we need to find out is what information exactly do we have in order to solve for this? Well, omega 1, so I'm going to call wheel 1 the wheel that was already spinning. So it has an angular speed omega p, right? The initial angular speed of the other disk is 0. So we have plus 0 is equal to 2 omega final, and thus omega final is equal to omega sub p, or the angular speed of the platform, divided by 2. So it wasn't a hard question, just you had to recognize that there was angular momentum being conserved. Alright, so we're approaching the end, we're almost at the end. And so it says that a student now uses the rotating platform. We're given the rotational inertia to find the rotational inertia of an unknown object about a vertical axis that passes through the object's center of mass. So we have a graph, and so it says on the graph on the previous page, draw a best fit line for the data. Okay, well once again, I don't have the graph over here, but I'll do my best to try and replicate it. So we have point 2, 0.8. So I'll draw lines. That's 1, that's 2, that's 3, that's 4, that's 5, and then that's 2, 4, 6, 8, 10. So it's kind of like a checkerboard, and so we have the point 2, something like that, around there. We have the point 4, 1.4, 6, 2.8. I'll label the graphs as well, don't worry. 8, 3.6. And then 10, 4.3, I'd say. Okay. Oh, whoops, I lost this middle one. Okay, so it's not the best recreation, but it's still manageable. Keep in mind that once again, this would be much easier because you're just going to be creating it directly on the page in the actual exam. So it says, for part 1, on the graph, draw a best fit line for the data. Okay. So we should be able to, I'll use a different color. Use blue. And with something like that. So you generally, when you're drawing a best fit line, if you have 5 points or 6 points, you generally want to have at least 1 point on the line if possible, and the same amount above and below it. And so that represents a fairly good best of line fit. Now there is a concept that you would learn in statistics called residuals, which is essentially the distance between each point and the line of best fit. You want to minimize the sum of all the residuals. You want to get the line that's best so that each point is close enough, is as close as it can be overall to the line. So we drew our line of best fit, and it says using the straight line, calculate the rotational inertia IU about a vertical axis as we're given. And so how exactly would we go about this? I'll write out, so I'll switch back to white. Okay, and so what exactly do we know? Well, we know that, sorry, let me just read this question again. So it's similar to the previous question, in which case the unknown object was dropped with its center of mass directly above the center of the platform. So the same idea applies, that it's a collision, so we conserve momentum. And so I'm not going to write, I'm just going to go directly to say it's I1 omega 1 plus I2 omega 2. This is initial. So this should be equal sign, not a not equal sign. This is equal to I1 omega 1 plus I2 omega 2. And this is final. And so on the actual IP exam, I would indicate that this is initial or final. For the purpose of this video, I'm just leaving it and explaining it by word. And so what we get is, similarly, we have IP, and then we have our omega. We have an initial speed of omega I. And then this is 0 is equal to, and then they both rotate together at angular speed. So it's similar to before, in which case we have our I sub P omega F plus I sub U omega F. Right? And so if we try and combine, we're trying to solve for IU, right? And so what we can do is we can do some simple rearranging. And so we can get IU omega F is equal to IP times omega initial minus omega final. And so IU is equal to IP times omega initial over omega final minus 1, right? Okay, I'm running out of space, so I am going to go on to the next line. I'll just remember this equation. So we had IU is equal to I sub P omega initial over omega final minus 1, right? So we have that. And so if we think about how exactly we can calculate our omega initial over our omega final, well, we have the graph, and so we just have to take the change in it. And so the change in omega initial over the change in omega final, using the line of best fit. Or we can actually just use a point on the line of best fit, because that should represent a coordinate, omega initial, omega final. We can just use that coordinate in order to solve. And so what we're given is that, so IU is equal to 3.1 times, with the line of best fit, you would find a 0.73 that works out very nicely, minus 1. And so this is equal to, putting it into my calculator, 4.13. And keep in mind the units for moment of inertia should be given in the question, in case you forgot, is kg meter squared. Alright, and so we solved for omega u. Now these last ones are just conceptual questions. So 3F says the kinetic energy of the spinning platform before is Ki, the total kinetic energy is Kf. Which of the following expressions is true? Okay, so once again, there's a very simple explanation that says it has to be less than. If you think about it, you could calculate it and you could prove, or you could just say that, okay, so they collide and they reach the same angular speed, right? Think about what that's characteristic of. An inelastic collision, right? And so because the center of masses are aligned, it isn't possible for you to have a greater amount of kinetic energy, so it's only possible for you to have less than or equal to, and because they reach the same angular speed, it's once again an inelastic collision, so Kf has to be less than Ki. I'm going to think on whether you can actually prove this mathematically. I believe you can, but let me just try and think about, I guess you could use just the fact that you could just use the formulas for Kf and Ki, saying that, okay, so the net kinetic energy at the end is going to be the moment of inertia, so Ip plus Iu times omega f squared. So we have Ip plus Iu omega f squared, and then versus Ip omega I squared, right? Or sorry, I guess you would have to calculate it separately, but sorry, this should be a 1/2. But essentially, the easy way, if you wanted to go through all the mathematics and prove exactly why it's less than, you could. The easy way to consider it is that it's just inelastic. Because what this mathematical proof would require you to do is to calculate, well, we know Ip and Iu, so you could put a numerical value there. And then you'd have to say, okay, well, if we consider omega f squared versus omega I squared, if you look on the graph, the axis of omega I is actually different from the axis of omega f. And so we see that for each of these points, and for all points on the line of best fit, if you calculated the slope, the change in omega sub I, so the initial angular speed, would always be greater than the change in the final omega speed. And so because of that, the square of omega initial would have to be greater than the square of omega final. And so you'd have to use that logic and then say that, okay, well, that difference has to be larger than Iu at all points. And so because of that, the initial kinetic energy has to be greater than Kf. Actually, I'll just write this down. So we see that omega I is always greater than omega f. If you calculate the slope, you should get something around, if I go back, something around like 2.2, 2.3 or so, if we use the line of best fit. And so we get something around 7/3, because remember, that's the point that we used. And so because of that, we know that omega I squared is greater than omega f squared. And so if we consider the slope as being 7/3, then our net change, so our difference between the squares would be greater than this, right? Because 7/3 is a value greater than 1, and so when you square it, it's going to be even bigger. And so because that, we can say that because omega I squared minus omega f squared is going to be greater than I sub u, our K initial has to be greater than our K final. Now, why did I use I sub u over here? Because essentially what happens is that we have our, if you distribute this out, right? If you distribute the kinetic final out, you get, you can cancel out the 1/2, so you get Ip Wf squared plus Iu Wf squared. And so what you find out is that this change in Wi squared minus Wf squared has to be greater than Iu over Ip omega f squared. So this is something you'd have to mathematically prove, and then you could show that K initial is greater than K final. But the easiest way is to just show that it's inelastic. The final question, 3G. So 3G says that one of the students observes that the center of mass of the object is not actually aligned with the axis. Is the experimental value greater than, less than, or equal to the actual value? Well, you should instantly be able to tell that this is greater than. Why? Well, because we have our parallel axis theorem. So our parallel axis theorem says that the actual value of the I is equal to our I calculated plus mx squared. And so if you think about it, the experimental value is going to be on the left, the center of mass, sorry, I should say, in context, IU is going to be I center of mass plus mx squared, and so because that plus mx squared is going to be a positive quantity, it has to be, because x squared is positive, our mass is positive, so IU must be greater than ICM. So that's just understanding whether you know the parallel axis theorem. So yeah, that marks the end of the 2019 AP Physics C Mechanics Free Response questions. Now, I will just point out, I'll go back, and I will just point out this important statement in blue over here. This is something that you should definitely memorize, that H is equal to L times 1 minus cos theta. You won't need the sine version of this, but the sine version would be, I'll put it in blue over here. If I remember correctly, it should be H is equal to L times, sorry, is it T minus sine T, I believe. That's the one. You very rarely, if ever, see that one, but that is one that you can research to find out the sine equivalent, but this one does come up. So H is equal to L times 1 minus cos theta, so remember that. Alright, so thank you so much for watching this video. I hope you guys understood some of the major concepts within AP Physics C. Sorry for the couple of slip-ups that I had, but if you want a time update, I got through everything in 1 hour, which means that the 45-minute time limit should be attainable for you guys, as long as, because you guys won't be explaining all the concepts or going through all the theory of it, you guys will just be answering the question. So yeah, once again, I hope you guys liked the video. Remember to like the video if you enjoyed and if you understood and got something out of it. Comment down below any suggestions that you guys might have for future content, and remember to subscribe and hit that notification bell. I will see you guys in the next video.